afternoon, everyone. Welcome to the class. Hello, everyone. Yeah, good to have you in the stream and in the chat. Hi. So we'll continue with our class today. This is I think, the eighth class we are having, and I think this module is going to be there's only one module left after this. So in the meantime, during the course between this module and the next module, there is significant amount of time. So what we will do is, I think we'll do some tests during the meantime. So I want you to review all the study materials that have been given, and yeah, we'll have one or two tests during this, in between the modules. Okay, I will send you the information and all of that. Okay, so in this module we are going to take a look at 2 or 3 things. I think we'll finish off with the manufacturing aspects, and we can jump onto other things that are there. Okay. Yeah, good afternoon, everyone. I see a lot of people in the chat boxes. Hello, all of you. Yeah, so let's start off today's session. Okay. So last time, Vaibhav, the tests, rough idea I don't have. So IIT is currently experimenting with a new system of taking tests. It's a kind of an online platform to take tests called Code Tantra or something. And we are experimenting with that. There are some issues that are being ironed out right now. And once that is done, we can kind of have the test. So maybe that will take this week or next week's time, something like that. So after that, I'll send you the details. Okay, so right, so we discussed about extrusion last time, and let's see what are the things that we discussed. Let me just okay, so we discussed how extrusion is basically pushing material from a cutout in a die, so that you can get these very unique kind of shapes and in long forms, and those shapes can be cut to do whatever, right? Okay, so the next is we discussed some of the uh, you know design considerations that you should keep in mind when you are thinking about designing for with extrusions, and we discussed that. And so these are part of that, and I showed you some of these raw materials which are available in the market to purchase, and each one of them are specifically designed as structural components, but you can use them for any purposes. Now along with such extrusions, you get hardware. So these channels that you see are designed in a manner that they would accept some nuts and bolts, heads of bolts or nuts. You could put it inside them, slide it inside these channels, and you can tighten. So those kind of hardware, ability to integrate it with hardware, those kind of things have been designed in such extrusions that you get in the market, like these ones. Okay, let me just move myself to the other side. Yeah, so these ones that I'm talking about. Okay. Right, so this is the chart that we had initially discussed, and based on this chart we were kind of taking a look at all of these different types of materials. So we discussed extrusion. Extrusion can be done in 2 forms. One is a cold extrusion, which is what you saw, and the other one is an impact extrusion. Okay, so impact extrusion is a different type of a manufacturing solid state forming process. So we will discuss that. I think if we have time in today's class, we will also discuss about how to bend sheet metal. Okay, and yeah, we will talk about another process called drawing and all that, and specifically we will talk about something called deep drawing. Okay, let's talk about impact extrusion first, and before we go delve into it, let's do like a reaction video of something. I am sure some of you must have seen this, but let's see how many of you get interested. This is the radiator that's there inside the computer, and you can see very clearly that it is an extruded piece of material with machined some parts which have been machined. But it is one of the first videos that showed you some of the background processing that happens when Apple manufactures its computers. And I hope you really liked that, because it was an interesting glimpse behind the scenes of how manufacturing of such devices on a mass scale is done. And the reason I was saying this is an infamous design is because it came out, I'm not sure, I think 2016, maybe, right? So during that time, and it was the pro version of the Mac computer, and it didn't perform as well as it should have in the market. However, the design was fantastic, and it was a very unique kind of chassis design. And yeah, they use some very interesting processes, and one of those processes is what we are going to talk about in this class. Okay, and that particular process that I'm talking about is called impact extrusion. Okay, and you can see the schematics. It's something similar to what Mac has done. Mac Pro was made with. Okay, so let's say you want to make something like this, right? So you want to make this kind of a piece, and what you do is you have this small blank. Okay, and that blank is put in a channel, and there are two dies. The bottom die has some form of cavity, and the top die kind of moves towards the blank with a significant impact force. The impact force is basically a large amount of force applied for a very small duration. Okay, so that's why it's called an impact force, because because I think the effect that such a thing has is much larger than what if you would apply like a force in a very slow manner. Okay, so yeah, it's pushed through, and the material comes out one by one, right? So you can see this kind of diagram, the photograph that it shows. Sometimes you would have some specific parts, such as these things called plates, stripper plates, which help in removing the part from the punch itself. So this punch kind of moves down, and because of the force of the punch, the material kind of flows and runs up the punch. Okay, so it moves up the punch, it flows up the punch, and that is removed, and that is the part that is desired. And this is what is the process that you saw in the Mac Pro video. The video is going to be there in the presentation if you want to access and see it later on also, right? Okay, so so the other very interesting manufacturing process, impact extrusion, is also used. No, it's not impact extrusion, but yeah, it's die forming. Okay, it's another type of forming process, and it's called deep drawing. So that was impact extrusion. So you used impact force to make the material flow up to the die and remove it. And this one is called deep drawing. Why is it called deep drawing? Is because it's kind of similar to the other one, but it's different in the sense that the force is not applied as an impact force, but rather it is applied subsequently, gradually. And the reason it's called drawing is because the material is drawn from a blank like this. Okay, And the idea is that the Coke bottle, the Coke can, this Coca-Cola can is formed using this kind of a process. You have a sheet metal of a certain thickness, and it's a die, a punch is pushed through the material, okay, and the material is held between these two, clamps right here, okay. You see this blank holder, and when it's pushed, this clamp portion does not move. The other portion which is between the punch and the blank, it kind of stretches and forms this kind of a shape, right? So after one operation this would happen, then the next operation would elongate it further, then the subsequent operations would elongate it even further, and you can get like very very thin sheet metal parts out of something like this. Finally, to actually make the can in the shape the can is, you would use some kind of processes such as necking and doming and seaming, okay. It's very interesting. The engineering behind this is very very fascinating, and there is already a video on the internet by a person, and I'll show you the video and we'll react to that video, I guess, right? Okay, let's see if there's a question. Is there a case where we use these methods for things, robots that are not cylindrical? Mostly these two processes are for cylindrical, use cylindrical dies, or somehow they'll have cylindrical symmetry. The reason is that if there are corners, then it becomes very difficult for us to manage the flow of material in such kind of intricate shapes, okay. So let's take a look at another video of how such cans are manufactured, okay. And this is a very interesting video. I'll pause in the middle and kind of give you my comments also, so that you can, it'll add to the learning, okay. So, or okay, let's see.
The ingenious
so
design
this one is
the aluminum beverage
ingenious
can.
design of the aluminum
Every year,
can.
nearly 500 billion of these cans are manufactured. That's about 15,000 per second. So many that we overlook the can's superb engineering.
So Bill Hammack has several books, I think 2 or 3 books, and also he has a fantastic YouTube channel where he discusses about various engineering processes and engineering, like really really not cutting edge, ingenious engineering problem solutions, okay, solutions to problems, okay. So this one is one video about the can, okay, and yeah, let's
start with why the can is shaped like it is. Why a cylinder? An engineer might like to make a spherical can. It has the smallest surface area for a given volume, and so it uses the least amount of material. And it also has no corners, and so no weak points, because the pressure in the can uniformly stresses the walls. But a sphere is not practical to manufacture, and of course, it'll roll off the table. Also, when packed as closely as possible, only 74% of the total volume is taken up by the product.
Yeah, I'll do that again.
Sphere is not practical to manufacture. Only 74% of the total volume is taken up by the product. The other 26% is void space, which goes unused when transporting the cans or in a store display.
So transportation is one of the very critical, efficiency in transportation is one of the very critical requirements that engineers and designers have to deal with, okay. So here naturally this is discussed in context of the cans, but for any other kind of design, product designs also, when you are designing products, you have to think about the packaging and how it would be transported. If you are able to design products in a manner that a large number of them can be transported in a small volume, you will decrease, it will have multifold beneficial effects, right? It's obviously simple beneficial effects, economic beneficial effects are there. You are able to transport more numbers in a single shot, but think about the environmental effects also. So if you are able to transport more number of products in a single trip, then the amount of energy that is required to transport is also minimized, right? So that way it's one of the key requirements for designers in almost all kind of product design exercises. Okay.
An engineer could solve this problem by making a cuboid shaped can. It sits on a table, but it's uncomfortable to hold and awkward to drink from, and while easier to manufacture than a sphere, these edges are weak points and require very thick walls. But the cuboid surpasses the sphere in packing efficiency. It has almost no wasted space, although at the sacrifice of using more surface area to contain the same volume as the sphere. So, to create a can, engineers use a cylinder, which has elements of both shapes. From the top, it's like a sphere, and from the side, it's like a cuboid. A cylinder has a maximum packing factor of about 91%, not as good as the cuboid, but better than the sphere. Most important of all, the cylinder can be rapidly manufactured.
Okay.
The can begins as this disc called a...
So this is the part that we are discussing here, the process of deep drawing. Okay. And as you can see, he's made a very nice explanation with the whole different stages of manufacturing processes, and this is what we were talking about. The first step in the deep drawing process is to create this kind of a blank. Okay. And the blank is just cut out from a sheet of metal. Okay.
Blank, punched from an aluminum sheet about 3/10 of a millimeter thick. The first step starts with a...
So it's important to notice the thickness of the material, right? So 3/10 of a millimeter. So it's really thin. Okay.
drawing die, on which sits the blank and then a blank holder that rests on top.
Right.
We'll look at a slice of the die so we can see what's happening. A cylindrical punch presses down on the die, forming the blank into a cup. This process is called drawing. This cup is about 88 millimeters in diameter, larger than the final can, so it's redrawn. That process starts with this wide cup and uses another cylindrical punch and a redrawing die. The punch presses the cup through the redrawing die and transforms it into a cup with a narrower diameter, which is a bit taller.
So it's somewhat analogous to something like forming clay, right? So in pottery, you would kind of shape the material in that sense. That means you have a larger volume of clay in one side of things, and then as the whole thing spins, you would give it a certain shape towards the top. And once you try to do that, when you try to do that, you are essentially making the sides of the material thinner and thinner. Okay, the same kind of thing will happen here. Okay.
This redrawn cup is now the final diameter of the can, 65 millimeters, but it's not yet tall enough. A punch pushes this redrawn cup through an ironing ring. The cup stays the same diameter as it becomes taller and the walls thinner. If we watch this process again up close, you see the initial thick wall and then the thinner wall after it's ironed. Ironing occurs in 3 stages, each progressively making the walls thinner and the can taller. After the cup is ironed, the dome on the bottom is formed. This requires a convex doming tool and a punch with a matching concave indentation. As the punch presses the cup downward into the doming tool, the cup bottom then deforms into a dome. That dome reduces the amount of metal needed to manufacture the can. The dome bottom uses less material than if the bottom were flat. A dome is an arch revolved around its center. The curvature of the arch distributes some of the vertical load into horizontal forces, allowing a dome to withstand greater pressure than a flat beam.
So this is an important part of especially can manufacturing, where if you did not have the dome, then probably the bottom part would bulge out because of the pressure of the fluid that's inside. Okay. Whereas because of the dome it provides some structural stability. You can see how thin this is, right? So it provides some structural stability also.
On the dome, you might notice 2 large numbers. These debossed numbers are engraved on the doming tool. The first number signifies the production line in the factory, and the second number signifies the body maker number. The body maker is the machine that performs the redrawing, ironing, and doming processes.
So from his statement, you can hear the whole process is actually done by a single machine rather than different machines, right? So all of these processes, probably one or two are done in a separate machine. Maybe blanking itself is done in a separate machine. However, these steps of ironing, drawing and ironing, and then the subsequent stages of ironing are all done in a single kind of a machine or a single machine. Okay.
These numbers help troubleshoot production problems in the factory. In that factory, the manufacturing of a can takes place at a tremendous rate. These last three steps, redrawing, ironing, and doming, all happen in one continuous stroke in only a seventh of a second. The punch moves at a maximum velocity of 11 meters per second and experiences a maximum acceleration of 45 Gs. This process runs continuously for 6 months or around 100 million cycles before the machine needs servicing.
So you can imagine the amount of production that happens, right? So the machine that produces this can produce something at 0.7 of a second, and the machine itself runs for around 6 months continuously before it requires any kind of servicing. Okay, so that tells you the amount of aluminum cans that are manufactured in the world. Okay. So
now, if you look closely at the top of the can body, you see that the edges are wavy and uneven. These irregularities occur during the forming. To get a nice, even edge, about 6 millimeters is trimmed off of the top. With an even top, the can can now be sealed. But before that sealing occurs, a colorful design is printed on the outside. The term of art in the industry is decoration. The inside also gets a treatment. A spray-coated epoxy lacquer separates the can's contents from its aluminum walls. This prevents the drink from acquiring a metallic taste and also keeps acids in the beverage from dissolving the aluminum. The next step forms the can's neck, the part of the can body that tapers inward. This necking requires 11 stages. The forming starts with a straight-walled can. The top is brought slightly inward, and then this is repeated further up the can wall until the final diameter is reached. The change in neck size at each stage is so subtle that you can barely tell a difference between one stage and the next. Each one of these stages works by inserting an inner die into the can body, then pushing an outer die, called the necking sleeve, around the outside.
So the reason that it happens in several stages is because the part has become so thin. I mean, because of these subsequent operations that happened prior to it, the material has become very thin. And what happens if you try to apply too much force and try to deform the material too much when it is so thin is that it will fold on itself and it will get warped. Okay, since you don't want that, so instead of doing it in one or two steps, several gradual steps are used to reduce this kind of diameter on the top. The same process, no, it's also used to make like water bottles. If you've seen these metal water bottles, so they have cylindrical shape and they have a curved neck at the top. So the same kind of operations are done in that.
The necking sleeve retracts, the inner die retracts, and the can moves to the next stage. The necking is drawn out over many different stages to prevent wrinkling or pleating of the thin aluminum. Since the 1960s, the diameter of the can end has become smaller by 6 millimeters, from 60 millimeters to 54 millimeters today. This seems a tiny amount, but the aluminum can industry produces over 100 billion cans a year, so that 6 millimeter reduction saves at least 90 million kilograms of aluminum annually. That amount would form a solid cube of aluminum 32 meters on a side. Compare that to a 787 Dreamliner with a 60-meter wingspan. Now, after
Americans kind of measure things like this, like they just like to compare it with football fields or airplanes. It's very strange. The question is, why doesn't the decoration get corroded while drawing the neck? So the neck drawing operation, if you saw clearly, it is only done towards the top part of the can. It's not done at the bottom. So that means the bottom, the sides of the can are fairly protected during these operations. So the necking operation only happens towards the top. So I think if you do it towards the later side, then you will not have a decoration which kind of goes and which curves, like for example, if you see in the video, so here the decorations kind of are part of this curve also. So if you had already done the necking operations and then gone for something like decoration, you would not get the designs in these curved parts very effectively. Okay, so that's the idea. Right. So
Now, after the neck has been formed, the top is flanged. That is, it flares out slightly and allows the end to be secured to the body, which brings us to the next brilliant design feature, the double seam. On older steel cans, manufacturers welded or soldered on the ends.
Now this is the very interesting bit that I like. It's not related to the manufacturing process that we are discussing, but it shows you the kind of problem solving and the creative engineering design that goes into the into such design of such cans. Okay.
Contaminated the can's contents. In contrast, today's cans use a hygienic double seam, which can also be made faster. This can is cut in half so you can see the cross-section of the double seam.
Okay,
to create the seam, a machine uses two basic operations. The first curls the end of the can cover around the flange of the can body. The second operation presses the folds of the metal together to form an airtight seal. While the operations themselves are simple, they require high precision. Parts misaligned by a small fraction of a millimeter cause the seam to fail. In addition to the clamping of the end and can body, a sealing compound ensures that no gas escapes through the double seam.
So here in the can industry, this kind of a process is used. But if let's say I want to give you a challenge. Okay, let's say if you want to make a box or a cylindrical, a bottle where water is stored, and it's not supposed to leak out. Okay, how would you design something like that if you want to completely, if the bottle is to be disassembled at the center? Okay, so let's say it's a cylinder and it's threaded at the center, these two halves are threaded at the center. Then how would you design this kind of arrangement so that it can hold very low density liquid at the in the inside also, so that it does not flow out of this? So I want you to search for something like that and tell me the answer if you can. Okay, what would be a potential
solution? Compound is applied
solution?
as a liquid and hardens to form a gasket. The end, attached immediately after the can is filled, traps gases inside the can to create pressures of about 30 psi or 2 times atmospheric pressure. In soda, carbon dioxide produces the pressure. In non-carbonated drinks like juices, nitrogen is added. So why is a beverage can pressurized? Because the internal pressure creates a strong can despite its thin walls. Squeeze a closed pressurized can, it barely gives. Then squeeze an empty can. It flexes easily. The can walls are thin, only 75 microns thick, and they are flimsy. But the internal pressure of a sealed can pushes outwards equally and so keeps the wall in tension. This tension is key. The thin wall acts like a chain. In compression, it has no strength, but in tension, it's very strong. The internal pressure strengthens the cans so that they can be safely stacked. A pressurized can easily supports the weight of an average human adult. It also adds enough strength so that the can doesn't need the corrugations like in this unpressurized steel food can. While initially pressurized to about 2 atmospheres, a can may experience up to 4 atmospheres of internal pressure in its lifetime due to elevated temperatures, and so the can is designed to withstand up to 6 atmospheres or 90 psi before the dome or the end will buckle. Why is there a tab on the end of the can?
So the rest of the video is interesting, is very interesting, especially this part where he talks about the design of this pull tab. Okay, it's a very, very interesting design. I will not, let's not see it here, but the video is there for you, and I think I will put a link in the OneNote drive also, and you can go ahead and look at this, okay, later on. Okay, so let's move forward. Okay, this guy is Bill Hammack, by the way. Go and subscribe to his channel, I guess, right? Okay, so let's take a look at another process, and this one is called spinning. And it's one of so now we have kind of slowly transitioned into the kind of manufacturing processes which are mostly used in sheet metal. Okay, so the first one was impact extrusion, which was not really used, which is not really for sheet metal but thicker blocks. But as you go towards sheet metal designs, then these forming processes are mostly used, and there are other processes also, like you know uh, which are not here, but there are a lot of forming processes for sheet metal. I think we'll discuss it in the next chapter of the course. But first one is here, it's called spinning, and the idea is that this is a very simple block diagram I've taken from a book. I think it's the Jim Lesko's book, if I'm not mistaken, and the idea is this only. So you have a mandrel, which is something like a die, okay, and the idea is that this part is curved, okay, and you want a sheet to wrap around this, okay. And how would you do this is you would have a clamp, you would have a sheet of cylindrical sheet of material, and you would clamp it at one end, pressing it against the mandrel, and then you would have this kind of a tool. You would have like a square block with a handle, and you would have some rotating, uh, a cylindrical disc like a torus, like a donut, okay. Somebody said donuts per bald eagle. Okay, that was funny. Madhav, no, Gaurav, right. So this is like a donut, okay, and this kind of, you can press the thing on the sheet metal, and the sheet metal kind of elongates because the whole thing is spinning. The sheet metal is spinning. This kind of elongates and takes the form of this mandrel. Okay, it's one of the cheapest sheet metal forming processes. It's the production time is also very low. It can be done with labor, skilled labor, but it can be done in a high tech operation also. Things like utensils, that many of the utensils that we see in our homes, no, they are made with the spinning processes. And the light, the domes of large floodlights, okay, let's say if you have like these large floodlights for illuminating a large area, let's say stadium lights and all, the domes that are there, those things kind of are made with spinning, okay. Right. So this is an example of that. I mean, this is a video that shows you that process. Now this is the mandrel, and you want the sheet metal to take this form, this kind of a stepped cylindrical form, and this one probably will be part of a light fixture, okay. This is the tool that I'm talking about. This is like a donut shape, and this tool is mounted on a structure on. So this whole operation is done, can be done on a lathe machine with the proper attachments like these mandrels and this tail stop and all that. And you'll see that it's a fairly labor intensive process, okay. So this is a lubricant that is put in so that it, so you see how it kind of, no, it's fine. I mean, you can be informal. Jokes are welcome, as long as they are, funny. So this is called spinning. Okay. And a person is operating it, and the way this is arranged, that is, it forms a kind of a lever. You pull on one end and push the other rod, so that it kind of digs into the material and pushes it against the mandrel, okay. Now there's a tool which is used to kind of cut a portion of it, and that portion is removed, okay. Now once that portion is removed, this becomes the light fixture. Okay, it's a very very simple process, but you can make these kind of cylindrical shaped objects, and naturally the material that it can manipulate is needs to be something which is a little more ductile and a little more softer. So softer steels and aluminum seems to be the better candidate for this kind of a process. Okay, and by the looks of it, it seems very rudimentary, but look at this design. This was done by some Ultimo Grito, and the product is called the Grito lampshade. And what he's done is he's made it with spinning, and he's retained a part of the spinning process which is kind of warped, and he cut the process, he cut the shape and bent it inside, and internally he painted it red. Okay, and there's a light bulb back on the inside, and it becomes like a beautiful lampshade. Okay, and yeah, what kind of things can be made with spinning processes? You can make balls also, like if you can imagine, you can make it in two halves and kind of make processes to join it. You can make things like bowls, caps, these kind of cones, these kind of funeral urns. We don't use it, but yeah, a lot of people in the West use this, something like this. It is possible to do secondary processes and make perforations, so that these pieces can become part of larger products. Okay, a lot of musical instruments can kind of be made with this. Like for example, this trumpet bass is made using spinning process. Things like venturi can also be done. As you can see, these long cylindrical parts can also be made using such process. Now this one, I do not endorse this video because it's not very safe working environments. This guy is probably somewhere from North India, or I don't know, maybe Pakistan. But we can see how it happens. Let's reduce the volume a little bit, because the sound really isn't important. So he's making what's it called? A traditional tumbler. I don't know what it, ghada. Okay, he's making a ghada. Okay. So Chaitanya is asking, can products made by spinning process also be made by deep drawing, right? Some yes, but something like this, for example, it can be done with spinning, but it can't be done with deep drawing, because the die, there's a distinct undercut and the die cannot come out of this, and the die needs to be solid for deep drawing, right? However, I think you can do it. You can do the deep drawing process is not like a single process. Okay, it's a collection of these different processes which was used, let's say, in the can manufacturing video of doming, ironing, and all these kind of various processes together form like the deep drawing process. Okay. The donut is kind of at the end of his tool. It was seen in the last video. What is it called? What is this thing called? If anyone can tell me the answer. So Cyril is asking if the material is thicker for spinning. Well, not necessarily. Okay, you can have various thicknesses. The thicker the material, of course, in spinning, since a very load intensive process, it requires large amount of force to be applied in a very specific manner. It's not done for very very thick materials unless you have like an automated machine. So Aditya is asking, if you have a strong machine, by strong I'm assuming that you are asking something like something can apply a large amount of force. Can you deep draw using other stronger materials? the main property that is required in the material to be suitable for deep drawing is its ductility. So it depends on the material's ductility. Okay. Uh, uh, okay. Okay. I think this kind of tells you how you can get like undercuts in a spinning operation. Okay. Right. So let's take a look at if there is anything. No, there's nothing. Okay, that was the last slide in the presentation, and that was spinning. So we mostly covered the these processes that are there. Okay, a spinning, drawing, bend. So bending we have not done. So we'll take a look at bending in the next this thing. Uh, right. Okay. Right. So let's go to the next set of slides. So wait, let me wait. Okay. Can you see it? Can you see? Yeah, you can see. We are not starting here. We are starting somewhere here. Okay. And we are going to discuss about we are going to discuss about sheet metal. Okay. So so now that you've seen the versatility of sheet metal, you know what kind of operations are possible, right? So for example, you could do forming operations to get these kind of surfaces. Okay, you can get like two dies that press together to give this kind of shapes to the material. Okay, you could bend it and you could join it in a manner that you could get box shapes like these. So for example, this probably is a chassis of a computer, and all these computer chassis are made with bending operations. Okay, different kind of bending operations. Look at this interesting little product, quite simple, made out of single sheet of metal. You would have you if when you unfold it, it's just a single sheet of metal, and you just fold it to get these kind of an interesting design. Okay, so what exactly is a sheet metal? Sheet metal is so it's kind of a it's not a very good clear definition, but it's mostly understood something like if a material is less than 6 thickness, then you by convention you would call it sheet metal. Okay, and uh, you have many kind of application areas for sheet metal, and most of the products, you before you kind of go into like machining and large kind of heavy intense investment kind of processes like casting, die casting and all that, you'd first explore sheet metal. Can it be done with bending, folding, or forming sheet metals? Okay, uh, there's a very famous case example, the Jaguar E-Type. I think it was made by a person in a shop by just hammering away sheet metal. Okay, it was made by a craftsman, and the whole it's a very very beautiful car. Let me just search for you what it looked like. Okay, if Google Chrome is there, let's see. Okay, yeah, wait, I saw it just a second. Yeah, so this is the Jaguar E-Type, and you can see how it's a beautiful car, no? So famously, this was done by a person, a craftsman, okay, and it was made not by like tools and dies when it first came out, but it was made by a by a by a team with just hammering away sheet metal and kind of joining it together. It's a very interesting case example. You can see it. I think I'm not sure, but this maybe the person went on to become like part of Bertone or something like that. I don't know. Okay, maybe I may be very wrong. Okay, so and don't quote me on that. Right? Okay, so let's take a look at the presentation back. Come back to the presentation. Where is the presentation? Where is my OBS? Where is my presentation? Just a second. I face technical difficulties often with this. Right. Okay. Right. Right. Okay. What kind of things do you need to take care of when you are looking at sheet metal? Designing with sheet metal are first and foremost something called formability. So the material, this is like a meta property. It is a property that encompasses several other properties like the ductility, the strength of the material, how much it can stretch, and how much are the yield stresses and the ultimate tensile stresses and all those things. So all these kind of contribute towards making something called wait, I need this sometimes, but I can't find it. So something called formability. Okay, and appropriate tooling can help you kind of design these kind of shapes. And what are the main kind of processes that are there? Shearing is basically cutting off the material. Scissor is a shear. Okay, how does a scissor cut paper? If you ever noticed carefully, then the shear kind of travel in a manner that it doesn't necessarily need to touch each other, those things. Although yeah, if it's better for thin materials like paper, it travels, the blades kind of travel against each other in like this, in a form like this. It travels like this. Okay, and because of that, the material kind of tears away, and this is called shearing. Bending is just bending of the materials. There are several different types of bending operations. Stretch forming is to form the material by stretching it. Imagine if you had a lot of force in strength with you. You could kind of take a piece of sheet metal and you could press it against a surface which has a form, which a mold which has a form, and it would be it would take the form of that. Again, we discussed about deep drawing. Stretch drawing is something similar to deep drawing, where instead of pushing the material, you pull it. Okay, you hold it in one end and pull it against something else. Okay, something similar to stretch forming. Press forming, and these kind of special processes are there which uses specific type of application of force. Okay, how would you apply force? Depending on that, these various different types of sheet metal operations are categorized. Okay, now before we move on to the slides, there are a few things that you should notice in some of these images, right? So first and foremost, you see these bends, no, they are never sharp. In sheet metal, no, it's not possible to get like a perfect 90-degree bend. It's not, definitely not possible, because you are bending eventually, right? So you need a radius. Okay, and the other thing that I want you to notice are these kind of holes that are there. They'll be there in these kind of corners. These are relief holes. So for example, if you are bending this part like this, okay, and if there was no hole, then when you are bending this, it would interfere with that. Okay, this bend would interfere with this bend and it will crumble. The material would crumble at this corner. Okay, so because of that, these relief holes are given. Okay, and the other things that I want you to notice are these small things. These are studs, and there are various types of studs, screws, fixtures, and lots of other things which kind of help you to design products using sheet metal. Okay, so the idea is that you would make various pieces out of sheet metal, and you join these pieces, and once these are joined with these various hardwares, then it would become like probably this kind of a product. Okay, probably this kind of product. Right, so let's move on. And what would you do when so let's say you want to make a sheet metal object. So how would you start? So naturally, where is my mouse? Okay, step one is to cut it into shape, and there are several ways in which you can do. Okay, so this is the shearing operation. This machine is there in our department also, and the idea is that you have like a punch which is there, okay, which and a die, and the workpiece, which is like a sheet metal, is held perfectly in place. Okay, and then this kind of comes down. Typically the workpiece is held very close to the edge, so that if it's not held close to the edge, then the shearing operation would not happen properly. Okay, so this same thing is given from the top this way. So if you look at it from, this is not the top, I think this is the front. Okay, not top, front. So from the front it looks like this, the punch is like this. Okay, so when the punch kind of comes down, you can imagine this gap between these two material kind of traveling from one end to the other end, because so imagine this is the base and this is the punch. When it comes down like this gap that you have between these two material, this kind of travels from one end to the other, and this kind of behaves the same way like you would use scissors. Okay, so this is like the shearing operation. Yeah. Sometimes what you would want is, you don't want like a cut, you don't want to shear it. What you want is like a blank of a circular blank. Okay, so in such cases you would have dies which are designed specifically for that. This would be a cylindrical punch. This is a die, and the punch would come down and it would cut the material from this and this sides, and you would either use this or you would use this, right? So whichever part is important. There's another variation there's another variation of cutting process which uses, instead of like a punch like this and like this, you would use rollers. So these rollers, you would, like pizza cutters, but instead of one pizza cutter there are two pizza cutters, and arranged in a manner that there's like a small angle and a gap between them, so material can be passed between them, and it will cut in that through, because of these rollers. Okay, and you have so this diagram kind of tells you a little bit about how you should think about the blanks. So the first step in designing anything out of sheet metal is to think about, okay, I want to make something like this, and when I open it up, it should be in a manner that the least amount of material is wasted from a larger sheet. Okay, so it's better to design something which has this kind of an interlocking cutting way, rather than something like this where a lot of the material is wasted. Okay, is the punch angled inwards or does it cut vertically? The punch in the first diagram, it kind of moves straight down. Okay, it's not angled. I mean, it's not angled. So if this is a punch, it's not like this, right? It's not like this. So but the edge itself is kind of cut in this manner. It's kind of tapered, and when it comes down straight. Just the edge kind of travels along. So I don't have anything to show you properly. Right, so I hope you understand from the images. Okay, just think about it a little bit, and well, okay, let's move on. I think mostly we discussed the points in this slide. Okay, and there are some considerations when you are cutting material. Like, for example, there needs to be some kind of clearance between the die and the punch. Okay, so there is if there is a correct clearance, then you would get a very clean cut. Okay, if there is a larger clearance, then you would get like a sheet metal which is cut, and at the edges it is like this. Okay, so this typically you don't want, because it will imply that you need to have another set of operations to cut it again at this end, right? Because this probably won't be of much use to you, right? So this design of this clearance becomes very important for such machines. Okay, and also for, let's say, when you're doing manually also, this kind of things become important. And when the material is cut, it's not like a straight, it's not like an edge. So that's important, because when we are designing it in, let's say, CAD or something like that, our edges are always flat, like 90 degrees to each other, right? So but in reality what happens, the part with where it is cut, right? So this is what you will see. So you would have this portion which kind of is pressed by the punch first, and there will be a straight section which is like the burnished section, where there was the largest friction between the material and the punch, and there will be a section where the tearing of the material happens. This diagram kind of shows you a little bit what actually happens from, let's say, the die goes from this stage 1 to 2, right, and then to 3, right? So this is what happens. So first there is a rollover formation. So this is the rollover. Okay, so the punch moves down, and this kind of material indents a little bit over here, right? Natural to understand, if you think about metal as something which is softer. Okay, then once the punch moves a little bit more, then there is some cracks that appear at edges of these punch, where this punch meets the material, and finally these cracks kind of propagate, traverse, and join together, right? So this is the crack that has happened there, and this section that you see over here, the burnished section, is this section, right? So this part over here, or this part over here, right? So burnished, so this is like a microscopic view of what happens at the part where it is cut. It's important to know this, because when you are actually designing things with sheet metal, right, you never want the edges of where it is cut by a punch and all that to be exposed directly to the outer surfaces, because these places are sharp. Where did my mouse go? So these places are sharp, which can easily cut the user. So typically what happens is that you do something like an hemming operation. HEMMING, right? Hemming operation is something like this, right? So you bend the metal like this, right? So now this becomes, it's cleaner, and you can have it exposed to the outer side or external parts of the product. Okay, right? So we'll mostly, this is discussed. And yeah, what is blanking and what is punching, right? So this, let's say you want to make a washer. It starts off with a simple sheet of metal, right? And that goes through a punch, and when you punch it, if you are using the part that has come out of the sheet metal, that operation is called blanking. After that, what you do is, this piece you take forward and you would punch again, and this piece that comes out of the punch, this is discarded, right? And this one is used, right? So when you are using the part that is not, that is not separated, right? That is the part, the workpiece itself, then this is called punching. I hope you understand the difference between these two. It's quite subtle, right? So in this one also it's the same thing. So let's say you want to, this is a piece of sheet metal and you are cutting, so that you want to use these gray areas which do not have lines. So this is a blanking operation. Now there's another operation where this is a piece of sheet metal and you want to remove this hole, right? And this will be thrown away and this will be used, right? So this is a punching operation. Okay, so these two are like simple differences. Okay, Okay, so let's talk about bending operations. So I want to go back to a previous slide just to see if you saw. Oh, this is what I was talking about. So yeah, right. So let's go forward, and now we are. Let's see the chat. Is the punch angle inwards or does it cut vertically in cylindrical punches? Even in cylindrical punches, what happens is that that's a good question, right? So what you mean is, let's say if there's a cylinder, if it's a cylinder, then the punches are whether they are like this or they are like this, right? So it depends. Okay, so sometimes when it is a material which is very much ductile, and there are chances that this kind of rollover portions in the cutting surfaces are going to be very large, right? So if this is how the material may get cut because of its larger what do you say, ductility properties and all of that, then you do use something like this. Okay, however, there are punches like this also. Okay, for smaller ones you can go with this. For much larger ones, I think these are more suitable, something like that. Okay, yeah, I hope that answers Gaurav's question. Right, so let's discuss sheet metal bending. Sheet metal bending is uh, one of the very basic kind of manufacturing processes, and a lot of products in the market are made using sheet metal. Okay, so some of the key things that you need to understand is that it's always good to bend metal across grains. So what happens is, how is sheet metal made? So we discussed in our prior class, there's some process called rolling, where you would have these two rollers and a thicker sheet of material is passed on from one end and a thinner sheet comes out at the other, right? And because of this kind of an operation, what happens, the grains kind of elongate. If there were grains which were much larger, they would elongate because of this operation. So you sometimes, if you don't do like the crystallization operations, you would get materials which are not recrystallized, right? So you would get these longer grain structures with some internal stresses that gives it hardness in a certain direction, or strength in certain direction and hardness along its surfaces. So for such material, if you're using sheet metal with such properties, then it's always a good idea to bend across grains. So if this is a sheet metal and if the grains are kind of aligned this way, it's always good to bend it like this. Okay, rather than bending it across the grains like this. Okay, I hope you understand from the sketches. So this is what this diagram says. So it's better to bend because chances are that you would form some cracks along these grain lines if you bend it along the grains. Okay, well, okay, right, let's discuss the specific bending operations. And the first one is like the V bending. It is like a very simple process of bending a sheet metal using a die which has a notch, a V notch. Okay, so there is a V notch here, and the sheet metal is kept on top. A punch with a similar kind of a positive shape is pressed onto the sheet metal, and you will get this kind of bends at location. So naturally, if you have a sheet metal like this, you can bend it along the whole length using these kind of processes. The other simple, one of the another simpler methods is air bending. Okay, and I am going to expect a lot of these kya bolte hain, airbender, last airbender jokes right here. Okay, and the way it works is, as you can see, it's a very simple schematic diagram. You have a punch and it comes down, and there's a force applied to the punch. It it comes down and the workpiece is not necessarily held in place. I mean, the gap that you see over here, no, it's a little too large. It's just for representation purposes, but it is slightly smaller than this. Okay, so you would press and you would get these kind of pressing operations. Now, before I'm flooded with all these other jokes, let's go forward. And edge bending. Edge bending is this kind of process where you want only the edge to be bent. So I can actually probably show you with a piece of paper. Do I have pieces of paper? Okay. I'm going to use one of the most useless things ever. This is like a business card. And if you want to do like edge bending, you put it on the edge, you hold it like this, okay, against my shirt. Let me go to a full view. You would have it like this, okay, and you would press against it, right? So you would press down and it would bend, okay. So air bending is if you hold it between two dies like this, and if you have a die of this shape and it is bent like this, so this is air bending, right? Well, right, okay. So do I need to move myself on one side? I think I should. Okay, so just to clarify the diagram, this is how it looks like. You have a pressure pad which holds the workpiece in place, right? And this wipes down this kind of a punch, right? It's called a wiping die here, it's not called a punch. I don't know exactly why, but these kind of terminologies varies across different manufacturing processes, right? So this wipes down and you get like a bend along the die shape, right? So you get a bend like this, right? If you want to, so one of the main problems for these kind of processes, so even for air bending, no, you could do like a acute bend, okay, you could bend it like a much larger angle, okay, but let's say for something like this, no, it becomes quite difficult. So as and when you keep approaching a certain kind of angles, you would find it difficult to control the punch because it becomes thinner and thinner, right? So you getting a like a very very sharp bend, it becomes difficult. However, some of those problems are negated by this kind of a process. It's called the rotary bending. Here the die kind of moves, okay, it can move across around this axis, the central axis over here, okay, so it can rotate around that axis, and when you force this, the die kind of rotates and takes the shape of the this rotary die takes the shape of the stationary die, okay, and you can get like these very acute angles, and of course you will not get like a 180-degree bend out of this, because that I don't think that will be possible in this process, but you can get like very acute angle bends. One of the things that you should know about metal bending is this, right? So you have this, you bent it, okay, and when I remove the force, what happens is that, let me full view. So what happens is that it, did you see, it comes back, okay? So I held it between this piece, I wiped it, okay, and it's supposed to retain this kind of shape. No, it doesn't, it will come back a little bit, and this is called the spring back of the sheet metal, and it is one of the key things to consider when you are bending. Let's say if you want to bend 90-degree, no, you need to bend the material a little more than 90-degree, okay, or little less than 90-degree, that means towards 0 degrees, okay, so probably something like 85 degrees, okay. So but these exact values depend on the material that you are using, okay. Let's say steel would have a much larger spring back effect than aluminium, okay. Yeah, So we are just going to go run through some of these, and I think this one is if you've seen, sometimes you get these kind of U channels in the market. You get these long channels which are made out of thin sheet metal which is folded, okay, and it clearly seems folded. It's not casted or it's not extruded, but it clearly seems folded because of the radii that are there around the length, along the length of the part. Okay, so this is how you make something like that, a channel. Okay, so you can make a channel of this U shape. Okay, something like this, using this process. The punch has a certain shape and the die has a certain shape, comes down and you get similarly in this same kind of a arrangement. If you use a punch which has a curved shape, you can get U bending done. Okay, because this particularly happens because of this clearance level over here. Okay, right. Okay, right. Technical details, this is very important. Okay, let me move myself to the other side. Can I move myself to the other side? I think I'll obscure. Let me be here itself. Okay, so there are how do I explain this properly? I'm thinking about it. So I want to sketch. Okay, let me do some sketching for you guys. Okay, yeah, and let me come to yeah, so let me come to this thing. Let me come here. Okay, and can you see what I'm sketching? Okay, if you can see, just say yes. Okay, right. So what I want to do is I want to create something like this. Let's say I want to create मैंने डिजाइन बनाया and I said कि I want to create something like this, right? And this is what my CAD looks like. It has sharp edges and all of these details. It's quite simple, and I wanted to make out of sheet metal. Okay, is it possible? It's not possible because there are some considerations that I have not thought about. So first and foremost, this kind of a sharp turn is naturally not possible in sheet metal, right? So you can imagine if this is thickness T and this is thickness T, at here it's naturally not thickness T, right? It's root 2T, right, which is more than T, right? Anyway, superfluous information. Let me increase the size of my eraser. More. So to make a part like this, what I would have to do is I would have to create a, let's say, let me give it some dimensions. Okay, and this is 2 cm and this is 2 cm, right? And this is, let's say, 5 cm. Okay, so and this width is, let's say, 10 cm. Okay, great. What I want to do, right, so I can start with a piece of sheet metal which is something like this, and this one is how much should it be? So this one is 5, 6, 7, 8, 9. Will I be able to make this part from this part? Actually, I won't be, because let's say I mark this kind of diagram. Okay, I want to bend it in normal material, simple process like air bending and all. So I will mark this. So I'll do. Let me do like a smaller brush size, and I'll mark this as 2 cm over here, 2 cm over here. Okay, fantastic. This is from here to here is 2 cm. Okay, imagine that this is 10 cm. Okay, it's not 10 cm, it doesn't look proportional like this, but yeah, imagine that. Or I can just change the dimension. Let's say this is how much? 4 cm. Okay, so imagine this is 4 cm. This is what I want to make. Okay. This is what I want to make. So I mark here 2 cm, I mark here 2 cm, and I mark here 5 cm. But when I bend, no, where do I keep that punch? So let's say I will do something like a wiping operation. Okay, so I have this kind of a setup, and I'll put the material over here, and I'll press the material with another piece. Okay, I'll hold the material where it is needed, and I will wipe it. Okay, so what happens is that even if I have sharp corners in the dies, no, I will obviously get a radius over here. Okay, so when I bend it, where should my mark be? Should my mark be here, or should my mark be here? From where to where is it 2 centimeters? From this edge to this edge, is this 2 centimeters, or is this 2 centimeters? What do I want? Okay, according to the design, the outer part is 2 centimeters, right? So I can't really mark it at 2 centimeters. Are you understanding? So what happens is that this kind of brings about this kind of a problem, no, brings about this necessity to think about some allowances that you need to consider when you are bending sheet metal. Okay, so let's do another layer, and let's hide this previous one. So now that I know what will actually happen in reality, let's say okay, so this is actually what is happening in reality, right? There will be one point from where the radius, this bending radius, will start, and there will be one point where it ends. Same thing on the internal side also. And if I can take, like in reality, right, if I take like a scale, or if I take like a vernier caliper, I can easily measure this distance, but I can't measure this distance. Okay, in reality I can't measure this distance, because where would I actually put that scale point? I don't know where the radius will end, right? So this part from over here to here, okay, or rather I should say, let me remove this. So if I take this line forward like this and like this, right, this point is called the mold point. Okay, and the distance from this mold point to this is called the setback distance. And now let's consider this internal area, and I know that it will bend along a circle, right? So there's a circle over here, and this radius of this circle is equal to something called bend radius. Okay, now here I want to tell you something else. So if I have like a straight piece, and let's say I bend this over here, so if this is something like what happens. So if this is what happens, then you can imagine what happened if this is the kind of bend that I did. So you can imagine what happened. The outer surface stretched, right? So it stretched because of this bend, and there is some kind of compression that happens towards the inner surface. Between this point and this point, right? This outer surface and the inner surface, no, there is like a central portion in this whole thing, okay, which is actually, so this line, right, the length of this line is actually the length of the flat sheet that was earlier there. On the internal side, it has stretched, it has shrunk from the actual length of the, let's say this was L. So this line, the length of this line is L. It has not changed after the bending operation. Whereas the outer surfaces, earlier maybe the outer surfaces, let's say if this is the thickness of the material, this is the material, right? So what has happened is, earlier before bending, this part, this line and this line both were L, but after bending, this part, this line from here to here, okay, and from here to here are not the same dimensions. They have changed from L, but because of this one part on the outer surface kind of stretches and the inner surface kind of compresses, there will be a central line somewhere where the length of the line would be the same as it would have been in the initial line. And incidentally, what happens is that this is the line where the stresses kind of change from compression to extension. So let's plot out stresses at this part of this bend. So what you would have it, let's say I will plot out, I'll say compression is this side, okay, this axis is compression. So this is what you will have the shape as the compression. The highest would be at this end, lowest would be at this end, and on this side it will be tension, okay, it will be something like this. These kind of diagrams are called bending diagrams in engineering, but here, just so that it's more visibly clear to you, I'm assuming that it's clearer to you like this. So this is what you will have. So you'll have this part in compression and this part in tension. Okay, so now let's go back to the slides. Okay, and let me first get my mouse to just a second. Right, okay. So now we can actually look at this diagram and kind of think about a few of these terminologies that are important in sheet metal bending. Okay, so First one is the neutral axis, which you see here. So this is the neutral axis. The neutral axis is the line where the transition from compression to stretching occurs. That means this internal blue part that you see over here, overall in the bend, is under compression, and the green part is overall in tension. But at this line, that is not there, right? And incidentally, because of that, this line is the same distance or same length initial as the initial length of the piece that was bent. Okay, right. Now this angle that is bending, this angle that you see, this is the bend angle, fairly obvious, right? Now there is something called K factor. K factor is important for you when you are designing sheet metal which are specifically made for bending and all that, right? So sheet metal parts which are specifically to be made with bending. K factor is the ratio of the distance between the internal surface over here to the neutral axis and the thickness. So the ratio of the distance between internal surface to the neutral axis and the thickness of the material. It is the, so let me get that. It is the ratio of distance to the neutral axis from the inside face to the thickness. Okay. Yes, so Tejas is right. Mostly in most cases, right, when you have a bending like this, the neutral axis will not be at the center point of the sheet metal. It will always be shifted to the side, to the internal side of the bend, okay, which is correctly shown in this diagram. So this is K factor, right? So K factor, let me again go back to my drawing. Where's my K factor equal to? So if this thickness is, let's say, distance to neutral axis is T and the sheet thickness is T, K factor equal to E by T. Okay, this is important. And the K factor, right? Yeah. So the K factor, it depends on your the type of material, okay, the type of sheet metal and the type of thickness that you have, okay. So the amount of thickness naturally that you can obviously see, right? It depends on the bending radiuses also. It depends on the bend angle, bend radius, and the thickness of the material, and it also depends on the composition of the material. Okay, so this is one term that you should know about. Let me clear everything. Now the other two things that you need to be clear about is bend allowance and something called bend deduction. Okay, so let's say you have a bent piece already, and this is the part that you've made, right? So you have a bent piece. Now you want to find out from this bent piece what should be the length of the blank, what should be the length of the piece. So let's say this one, I should draw it properly. Let me make it clear. So let's say this is the piece, and what I'm doing is, what I want to find out is what should be the flat from which I will make this part. Okay, where should be the line, what should be the length of this. So to calculate these kind of dimensions, the dimensions of the blank or the dimensions of the bend part itself, you would need to use two values called bend deduction and bend allowance. Bend allowance is the material that you will have to add to the initial length of the flat sheet in order to arrive at the length of the formed part. Okay, so this here is the formula for the bend allowance. Okay, I'll not go into explaining the formula, but what I will do is I will give you some videos where this is more explained in more depth, because we'll not have so much time, right, to kind of derive these formulas and all that. So, and this is bend deduction, right? So 2 times the setback distances minus the bend allowance, and this is the formula for the bend deduction, right? Bend deduction, what exactly it is? It is the material that you have to remove from the total length of your flanges in order to arrive at the flange length. So that means if I have, so this line over here that you see, so let me take another color. How much length you would need? So imagine this length is L dash. How much you would need to reduce from this? How much you would have to deduct from this length to arrive at the length of this blank? Okay, let's say if this is L. So L double dash minus bend deduction is equal to L, and L plus bend allowance equal to L double dash. So this is the basic idea of these two terms. But of course, there's a little more to all of this, and I would really want you to understand this by understanding the derivations for these. Okay, it's very, very simple mathematics, and you'll all be able to easily follow it. So don't worry. Okay, so I'll keep it at this, and let's see some of the chats if there are any questions, because I'm sure there will be. Till now, not any, except for Tejas, which I answered. Okay. So, right. Where's my... I'm sorry. My mouse just runs all over the place. Anyway, okay. Right. So, so that was about the sheet metal, some of these terms which were important to you. And besides that, I mean, sheet metal in the most advanced kind of processes that are used in sheet metal have taken the shape of something like this, like honeycomb structures and these kind of structures which are used in airplanes and all of that. I've kept this image for you to know that there are these kind of metamaterials also available, but we'll not discuss this kind of corrugation techniques and all that, except for probably one. I think I have one. So how would you create something like let's say this, right? So this piece over here. So it's very interesting. You have an aluminum sheet metal which is passed through rollers, and you get these kind of corrugated shapes. When you join it together, you could weld it at certain positions. You get this honeycomb structure. You cut a piece of it, okay, and you place it between two sheets of material, okay, and that becomes your honeycomb structure, and that is very, very light and really, really strong. Okay, you could make this out of paper, and you would realize how strong such a material configuration is. There's another way of doing it from sheet metal. You make something like this, you punch holes and you bend it at the right locations, okay, and that bend you could sandwich between two sheets like this, okay, and you would get this kind of a corrugated, I think it's called a sandwich structure. So you can get this kind of structures, and you could do a little more than that. So there are some operations where you would fill the cavities with foam, aluminum foam, or other kind of foam like ceramic foam, to enhance, let's say, the thermal properties of the material, or acoustic properties of the material, or even the strength of the material. Okay, so this image shows you that. So this is the direction, like the advanced side of all of these things. It's very interesting to see such things, right? Okay, others I will not go through, because they are kind of very, straightforward. And this is what I was talking about, hemming operations. Okay, let's take a look at some of the more exotic ones. It's very interesting. So one is tube bulging, where what you would do is, so you would have a die which is in two parts, like this and like this, like you can separate out. You have a cylinder which is closed, and you fill it up with fluid, and then a punch kind of moves down, and it creates this kind of a bulge, right? And this, you can imagine, you can make something like water bottles with something like this, right? It's a technique of getting these undercuts in the design, right? So this techniques of getting these weird shapes which will probably not come out of the die if you do it with typical processes. Well, uh, right. So this is important. This is not a manufacturing process, but it's a way of joining sheet metal. Okay, so this is basically, there's a if you pierce the sheet metal in a certain way, you get this kind of a flange where you can attach different screws and hardware to, right? So you'd have this, let's say this is the sheet, you would have a loaded stripper, and you would have a piercing punch which goes into this kind of a die block. Okay, this kind of an arrangement. Some part is eliminated, which is typically called a slug, and whatever part is formed over here, it looks like this. Now here you could put in a screw and you can thread it. Okay, right. I don't know if you've ever tried bending a hollow tube. It's not as easy as it seems. You can't bend hollow tubes just like that, like typical processes. When you bend the internal part of the tube, where the bend radius would be there, the internal part of the bend radius, right? That will collapse onto itself. Okay, and I should get these kind of props to show you, but anyway. So for that, you have these special kind of arrangements to bend tubes, and the idea is that you need to hold two ends of the tube in a very strong manner, like through using these chucks and all that, using some clamps and all that, and these forming blocks would force it themselves onto the tube. Okay, to stop the tube from collapsing, you would put these kind of mandrels. Okay, these are flexible pieces which provide structural stability to the pipe when it is being bent. Okay, these kind of, and bending a tube, right, bending a pipe is a forming operation. It's not really a bending operation. That means you would have to stretch and give it that shape instead of just collapsing it onto itself. Okay, and these are the three types that are shown over here. One is stretch bending. You'd stretch it, and then this forming block would be this stretched pipe would be pushed onto the forming block. Okay, and the forming block is fixed. This is draw bending, where the block itself kind of rotates along with the pressure bar, so it kind of behaves like a wiping process of bending. And this is compression bending, where this is forming block is fixed, and there is a metal piece which is a wiper which kind of takes the pipe and pushes it along the lines of along the forming block. So we have very recently we purchased like a pipe bending machine. So when you come back to the campus, you will be able to explore those machines. Okay, right. This is another very interesting and exotic manufacturing process, which is called hydroforming. And the idea is that there's a very large tank, and beneath the tank, there is a membrane. There's something made out of rubber, and the between the rubber and there's this kind of a die, a supporting block. There'll be the workpiece which is fitted and a punch which is fitted. The punch would travel into the rubber piece, and consequently towards the liquid, and the pressure from the liquid kind of forces the rubber diaphragm onto the punch, right? And you would get this kind of a forming operation. It's very, very interesting, and very large dome structures are sometimes made with this. And this other method, which is the most dramatic one, I think, which is called the explosive forming, where you would have a mold, you clamp the mold in one place and fill the whole tank with water, and you would have an explosion go off. The explosive, shock wave kind of pushes the sheet metal onto this die sheet. Okay. This is one more where electromagnetic, if the material is has some ferromagnetic properties, you could do something like this, where you have this kind of a cylindrical shape, which is the workpiece, right? And this is the mold that is there, where the cavity is there. Okay, in this cavity the material is supposed to be formed. You would charge the coil inside the whole thing, and this would induce eddy currents into the part, which would again create like opposing magnetic forces into the material, and the material itself would be pushed outside. Okay, so that way it's a very interesting process. Maybe you can read about it a little more. Okay, so what time is it? Okay, we can take 10 minutes to discuss some of the simple design considerations that you should think about. First and foremost, thickness is something very very important for sheet metal design. Okay, so the first thing is that whatever dimensions you think about, you should think about in terms of the thickness, the ratio to the thickness. Okay, so for example, if you are trying to place a hole, it's always a good idea to leave at least one thickness or two thickness gaps between the edges, from the edges to the hole. Okay, so like this. Otherwise what happens, there are chances that there will be cracks which operate here. Naturally you would want a hole to put in a bolt or something like that, no? So if you have it too close to the thickness, then through the edges, then it would crack from these parts. Okay, similarly you would want, if you want to put a hole at a vertical flange, okay, this kind of flange arrangement, you need at least two thicknesses, 1.5 to 2 thicknesses high from the bottom, from this face. Okay, it's always a good idea to have holes in the sheet metal which are larger than the thicknesses of the material. This is like a thumb rule that is there. And finally, if you have two holes, it should always be ensured that you have at least 2 to 3 times the thickness gap, which is 2 to 3 times the thickness of the material. Okay. Okay, this is very interesting actually. Okay, so let's say you want to make this kind of piece. Okay, and what you want to do is you want to pass a straight rod, which is supposed to have some kind of, which is supposed to be supposed to rotate. Okay, and naturally when you are designing, you really don't think about it. But how do you ensure that you are drilling this hole and this hole in such a manner that they are perfectly aligned? Okay, when I say perfectly, is as perfectly as possible. What do? Do you start off like this, where you have a blank, you drill the holes and you bend it? Chances are that the bending operation will misalign the holes. Okay. Similarly, you could do something like this. You start off with a blank, you bend it, and then you drill it. Chances are that because of the drilling operation, because of how you hold it, you would get good alignment, but the bending and all that would, the angle at which it is bent, those angles would go for a toss. So if you want to get some kind of accurate results, you should give some leeway for errors to happen. Okay, so this is one very interesting way. So what you could do is one piece you could make proper hole, and the other part you can make a hole in the form of a slot and in the direction in which you think most likely the misalignment will happen. Okay. The other way is that you could make like a pilot hole, and you so the way in which this is done is that you ensure that the distances from this pilot hole to this all these distances are accurate, and then use this pilot hole to clamp it onto the right surfaces in a proper manner and then drill it. There are of course other processes, but these kind of things are very often seen in product designs, okay, where you want to minimize the errors without increasing the necessity for it to be manufactured in a very controlled and accurate way. Okay. Okay. There are some other design considerations, like if you want to have like gaps like this, you should always ensure that they are at least greater than some thicknesses. Similarly here, right? So thickness is a very important parameter, as you can see. So typically what happens is that when we design in CAD, no, we don't think about such things. Sometimes what happens, we'll just make like the bend radius coming out of this. This is not possible, no. Can you see here? It's not possible. How do you cut something like this? Okay. So what you do is you can move this cut up a little or down a little. Cut the radius or cut the flange only. Okay. Right. Now these are some types of flanges that are there. You could make so unlike paper, bending paper does not stretch. Metal however stretches, right? So you could get like a straight flange, but you could also get these kind of stringed flanges and all these kind of things also. Okay. But however, you need to consider how the material kind of flows, and you have to think about if there are some tears which may happen, and if such things are happening, then provide relief holes where such problems may happen. Okay. Okay, right. And the way you would fasten sheet metal is something like this. So one is to weld it, and there's a very specific process for sheet metal welding which is called spot welding, where you would weld it only in one spot, and it's very common in automotive industries. The other way of fastening is to add a screw. There are sheet metal screws, specifically designed sheet metal screws. You don't need to add threads into the sheet metal. The sheet metal screws are designed in a manner that they will cut the threads onto sheet metal. Okay, they are harder than the material themselves. You could also think about some ways in which the sheet metal itself acts as ways of fastening, like for example in this one, and in these ones. And you have some ways in which you could add hardware. So like for example, this one is a special type of stud that can be fitted onto sheet metal. So you would have it on one end, let's say the holes are drilled in the right dimension, and once you tighten the bolt, tighten the nut, this whole thing kind of digs into the sheet metal. Okay, and these teeth dig into the sheet metal and holds it properly. So this way it doesn't move, and this becomes like a permanent, almost like a permanent joint. Okay, right. These are some more ways of fastening. There are hundreds and hundreds different things, and the way to find this is to go through something called manufacturers catalogs. Okay, so there are numerous manufacturers of sheet metal fasteners, sheet metal themselves, and you can go through catalogs on site in the, where is Chrome? Okay, so let me, it's called this, it's called McMaster car. Are the frames dropping or something? Is it okay? Can you see it? So this is a supplier of various kinds of, you know, hardware goods and components, and there are all kinds of things over here. Okay, and let's say hardware, machinery hardware, door and cabinet hardware. Let's take a look at cam latches. These are all the different types of cam latches that are there. Okay, this one seems interesting, or let's say this one seems interesting. I can click on this. I can go here. These are the different dimensions that are available, and once I click on this, I can download the CAD of this and actually add it into my CAD model. Okay, so yeah, so I can do like, what do I want? So typically you can download like step file. It opens in all things. So this step file is available. Now I can add this hardware directly into my models. And you can find almost everything there. So can I find screws? Can I find anything sheet metal? Hand tools. Okay, let's see. Hardware. Right, I don't know if there are screws here. Fabricating. Drill bits. Okay. Clamping vices. Positioning arms, let's say. Yeah, well, go ahead and explore all of this. It's very, 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 very interesting. Okay, anyway. There are some things for suspending and plumbing and oh my god, so many things. Okay, anyway. So that is McMaster car for you. And let's go back to our slides. And yeah, I think we are coming quite close to finishing this whole thing. Let's keep this for the next class. And yeah, despite how, you know, simple sheet metal looks, you can make like really, really cool designs out of it. These are some of the examples of minimalistic products that have been designed with sheet metal, and there are some which are quite famous, like these chairs. However, these are made out of acrylic, not really sheet metal, but this one I really, really love. Okay, uh, this is a chair which is made out of single piece of sheet metal. You can see this is the layout of the sheet metal. So first what is done is you take a sheet metal, you give this kind of a groove to it, you form it, right? And this operation imparts a certain amount of strength to these flat surfaces. Now when you bend it, no, it looks so simple and it looks so fragile, but look at this, right? Each one of these is 25 kgs. 1 2 3 4 5 6 7 8 9 10 11 12. Man, that is 300 kgs right here. Okay, so you can imagine how strong this chair is, and it's not made out of very thin sheet metal, but by the looks of it, it should not support so much weight, no? So this is what ingenious design in sheet metal can do. Okay, besides that, naturally you can fold it in the way in an origami kind of shapes and get very intricate designs and all that, even in architecture. Okay, so there is no assignment for this was from a previous thing. So okay, let me just see what was the assignment that I wanted to give. Okay, right, there are no assignments for this class. We will discuss some other manufacturing processes tomorrow and give you the assignment for that. One will definitely be a product design using sheet metal, and there'll be another one also. So yeah, so that is about it. Let me go back. Oh, you guys didn't see. I hope you saw this thing. Ah, so this was the chair that I was talking about. Okay, all these products. Okay, anyway, so we'll stop the class here today, and we'll discuss from here on onwards with some other manufacturing processes. We'll discuss tomorrow, and then we'll see what we'll do on Saturday. Okay, so thank you so much for joining, and it was good to have you in the class. Whoever there are remaining, let's see, कोई भी नहीं रहेगा शायद, I think. Okay, so whoever there are, thank you for joining, and yeah, the video is there for you. You can watch it at your own pace later on also. Let's hope there are no frame drops and all that. If you have any queries, please feel free to call me or send me. Don't send me email, but rather I would be more happier if you can put your queries in the OneNote file, so someday I can just go through those and I can give you feedback. Okay, so thank you so much everyone. Thank you, whoever is there. Have fun with the rest of your days, rest of your time today, and remember that this I hope you are not having other classes apart from, let's say, HSS or something. Are you having other classes? So spend the time that you have during the day, before the class and after the class, if possible, on doing the assignments. Okay, so thank you so much, and yeah, have fun. Okay, thank you.